Welcome to the absolute value function video. In the last video, we looked at the definition of absolute values. Now we're going to focus on absolute value functions, and this is a function that involves the absolute value of a variable. So let's compare between y equals x and y equals the absolute value of x. If I'm looking at y equals x, if I have x equals -3, my point for y is also going to be -3. If x is -2, then y is -2. Then -1, 0, 1, 2, 3. This is the point. These are the points for y equals x. Now, y equals absolute value of x. Remember, the absolute value of a number is the distance of that number to the number line of 0. So if I'm taking the absolute value of -3, the distance away from -3 to 0 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1, 0, 1, 2, 3. So let's just graph our linear graph first. We certainly know what this picture is going to look like. Straight diagonal or oblique line with a slope of 1. So this is y equals x. For y equals the absolute value of x, and the positive side is going to look the same. So it's kind of a line there with the purple, but on the other side now, all of our y values are positive. So it's going to look like this. So the purple is our y equals absolute value of x. It looks like a V. And then our linear graph y equals x is the oblique line. So the absolute value of function has the form y equals absolute value of f of x, where f of x is some function. So y equals the absolute value of x is just one variation of an absolute value function. The x-intercept of the graph of y equals f of x is a critical point. The graph of y equals the absolute value of f of x changes direction at this point. So if we look at our graph, our critical point is at x equals 0 because that is where our graph changed direction. Invariant point is the point that remains unchanged when a transformation is applied to it. The invariant point of an absolute function is the x-intercept of the original function. We could also express our absolute value function into a piecewise function that kind of looks like this. So you would say the absolute value of x can be x if our x value is greater than 0, and when going back to our graph, we can see that on the right-hand side, this portion of this graph looks like y equals x. And the second portion of our graph here, this looks like y equals -x. So that is where our piecewise function is coming from. Looks like -x if x is smaller than 0, or if x is negative. This is a very important part because we are going to use this piecewise function to describe what an absolute value function can look like. Since the absolute value of x cannot be negative, the part of the graph of y equals x that is below the x-axis is reflected in the x-axis to become y equals -x in the interval x is smaller than 0. And the part of the graph of y equals x that is on or above the graph is 0 or positive and remains unchanged as the line y equals x in the interval. That just recaps what I just said about our piecewise function, that if you take a look at our picture of y equals the absolute value of x, we see two portions. This portion is y equals x. This portion here is y equals -x. Now let's look at an example for us to graph. So we have the absolute value of 2x minus 3. The first thing I'm going to do is determine the y-intercept and the x-intercept. For your y-intercept, we are going to set x equal to 0. So this is 0 minus 3, which is the absolute value of negative 3, and that is 3. For our x-intercept, we're going to be careful here. We're going to set y equals to 0. But I can't just get rid of the absolute value sign. By definition, the absolute value of 2x minus 3 have to be split into two cases. It's going to be 0 equals 2x minus 3. That's one case. And the other case is 0 equals negative 2x minus 3. And that's by definition of absolute value. Now we're going to solve for each. So we're going to have 3 is equal to 2x. If I move the 3 to the other side, then I'll divide both sides by 2. X is 3 over 2. We're going to do the same thing. We'll distribute this negative, so it's negative 2x plus 3. Move the 2x to the other side, divide both sides by 2, and we just get the same thing. This means that our x-intercept is just going to be at 1.5, which is 3 over 2. Part B, we're supposed to sketch. The first thing we're going to do is sketch what we have from A, which are 2 points so far, and then we're going to find other points. Okay, so we have a point at 0, 3, which is our y-intercept. And then for our x-intercept is at 1.5. These are the 2 points we have so far. We're going to now look at other points. I'm going to draw a table of values. And I'm going to take a look at the other side of x equals 1.5. Our absolute value function is symmetrical, so if I know that there's a point at 0, 3, that means there should be another point at x equals 3, and we can look for that. Now plug it into my original function, which is absolute value of 2 times x, in this case is 3 minus 3. That's 6 minus 3. Absolute value of 3 is just 3. So we have a point at 3, 3. This is enough points for me to connect our graph. Now I'm just going to extend it a bit like this. And that is our absolute value graph. Take a note that our invariant point or our critical point is x equals 1.5. If we wanted to obtain this, you can see it right away that in order for this to be 0, we would need 2 times 3 over 2 minus 3 to get 0. And this would give us our invariant point. Very similar of how you would probably read the vertex of a quadratic. Next, we're going to look at our domain and range. We can insert any x value we want into our function. For our range, you can see that our lowest y value is 0, and then it goes up from there. Last question, we're going to express this as a piecewise function. So this is going to look like something like what we have here. In this case, the absolute value of 2x minus 3. Our first portion in the positive direction is going to be 2x minus 3 when x is greater than 1.5, which is our invariant point. It's going to be minus 2x minus 3 whenever x is smaller than our invariant point. These over here is coming from my case 1 and case 2 of my x-intercept calculation. So we get the positive 2x minus 3 on the right side of our invariant point, and then we get negative 2x minus 3 on the left side of our invariant point. And another way to look at it is just to look at the graph to determine how we're going to write our piecewise function. Let's try another strategy to sketch a graph. And this is to sketch a quadratic function. So we have the absolute value of x squared plus 2x minus 3. We're just going to find some of those y values for our original quadratic, and then we know to change our y values so that they are all positive afterwards. So I'm going to go ahead and plug in negative 4 into our function to see what we get. So that's 16 minus 8 minus 3, which is 5. That's 9 minus 6 minus 3, which is 0. We get 4 minus 3, which is minus 3. This is negative 5, and then I'm just gonna write in what those y values would be if you were to plug in those x values. Okay, so for my absolute value portion now, I'm going to take the absolute value of 5, which is 5, the absolute value of 0, which is 0, the absolute value of negative 3, which is 3, the absolute value of negative 5, which is 5, absolute value of negative 3, which is 3, then we get 0 and 5. So I'm just taking the absolute value of all those y values. Now we can graph these points. Okay, so we have a point at negative 4, 5. Our next point is at 0, negative 3, 0, 3. We have a point at negative 3, 0, negative 2, 3, negative 1, 5, 1, 0, and 2, 5. I'm going to connect these points from left to right. And then extend on each side. So this is what our graph looks like. If you think about what really happened here, what our vertex usually would have been, looking at this graph, would have been negative 1, negative 5. Which would look something like this. And then our points would connect to our x-intercepts. So if you look at the dotted part and the two end behavior lines, we would have a parabola. But all we really did is move anything that's underneath our x-axis up. And that's how we obtained our absolute value graph. I want you to try the next one on your own. Follow the very first example we did together to find the x-intercept and the y-intercept, and then press play to go through the solution. So for your y-intercept, we are just going to set x equal to 0. That would be 0 plus 0 plus 8 in the absolute value. absolute value of 8 is 8, so that is 1 point we have so far. Then we're going to find the x-intercept, and there are 2 cases according to the definition. So exactly negative x squared plus 2x plus 8 is equal to 0. And then I factor out the negative so that I can factor my quadratic. And once I did that and solved for 0, x is equal to 4 and negative 2. So those 2 are my x-intercepts. I need to check it one more time for case 2. For case 2, we're just going to negate what we see inside of our absolute value, which is negative times negative x squared plus 2x plus 8. And then I simplify the negative and factor it again, and we also got this very same x-intercept. Most of the time you will get the same x-intercepts anyway when you do the 2 cases, but it's always good to check. Now I'm going to go ahead and graph this on our grid. So there's 3 points we can graph. We have our y-intercept at 8, and then we also have our x-intercepts, one at negative 2, the other one at 4. Now we need to find more points because it's not enough. I just use x equals negative 3, x equals 1, and x equals 5 to find more points. And I plug them into our f of x. And I got negative 3, 7, 1, 9, and 5, 7. Then I'll connect the points from left to right. Don't draw your graph pointy because you know quadratic is not super pointy, especially with the parabola part around your vertex. So make sure that you actually have a curve going around your old vertex. So that is your graph. Our domain can be anything. Our range, our lowest y value is 0, and it goes on to infinity. Lastly, we're going to write our function as a piecewise function. Our invariant point is located at x equals 1. Now we're going to write the piecewise function for this graph. Got to be careful about this. There are 2 variations just looking at case 1 and case 2 of our x-intercept. For case 1, we should have an upside down quadratic because of the negative from the x squared. So that is going to look like the space between, or the x values between negative 2 to 4 on that interval. Then if you look at case 2, we would get an x squared minus 2x minus 8. This has a positive value in front of the x squared, which means we have the right side up quadratic. So when I'm writing out our piecewise function, we're going to have negative x squared plus 2x plus 8, which is on the inside of our absolute value. And the other one's a negative x squared plus 2x plus 8. Now we just have to write down the interval that this occurs on. So remember, this is an upside down graph. This is what it will look like. We see an upside down version of this in between negative 2 and 4. And then for the right side up, this part of the graph, this looks like that from infinity to negative 2 and from 4 and on. I can express this as set notation. So x is smaller or equal to negative 2, and this occurs when x is greater or equal to 4. And that would be our piecewise function. I want you to try the next one on your own as well. It's very similar. So go ahead and try that, and then when you're ready, press play for the solution. Okay, so you want to determine your y-intercept and your x-intercept first. For your y-intercept, we put in x equals 0 into our function, and we got back y equals 2. Then for our x-intercept, we're going to set x squared minus x minus 2 to 0, and also the second case where we have a negative in the front, we set that to 0 as well. Then we want to factor, and we would find that our x-intercept is 2 and negative 1. Then we can go ahead and graph this. So here's our y-intercept. Here are our x-intercepts. So I graphed the intercepts. Now we need to find more points. I calculated 2 other points, which is at -2 and 3, and I plugged it back into our f of x to find our y value. So we have points at -2, 4, and a point at 3, 4. Now I'm going to connect our points from left to right. Looks something like this. You can add in your arrows at each end. Then for your domain, it's from negative infinity to positive infinity. Your range is from 0 to infinity. Then lastly, we will write our piecewise function for f of x. So there's 2 components to this graph. It's going to be x squared minus x minus 2, and also negative x squared minus x minus 2. We're going to see when this occurs just by looking at our graph. So remember that because our x squared is positive, there's no negative in the front, this is what this graph is going to look like. And then for negative x squared, it's going to look like this, like it's going downward. So we see our arms going upward from here and here. So if you look at that interval, it's when x is smaller or equal to -1, and when x is greater or equal to 2. Then for the down portion of the graph over here, this occurs between -1 and 2. And that's it. For our very last example, I'm going to do this one with you. We're going to find the absolute value of -3x squared minus 1 and graph it. The first thing we're going to do is find our y-intercept. So I am going to set x to 0. Then we're left with the absolute value of -1, and this is 1. Now we'll look at our x-intercept. I'm going to set y equals to 0. And there are 2 cases we need to consider. That's -3x squared minus 1 is equal to 0. The second case is -3x squared minus 1 is equal to 0. So I'm going to move the 1 to the other side and then divide both sides by -3. We're going to get no solution here. I can't take the square root of a negative number. So that means there's no x-intercept. I'm going to try it for the other one and see if it's any better. Move the 1 to the other side. Divide both sides by 3. Again, I would have to take the absolute value of a negative. I'm going to have to take the square root of a negative number, and that yields no solution. So there are no x-intercepts in this case. The next thing we're going to do then is find other points. We only have 1 point so far, so I'm going to graph that later. And I'm just going to pick x equals 1 and x equals -1. I'll put it into our f of x function. So this is going to be -3 minus 1, which is -4, and the absolute value of -4 is 4. Now I'll do it for x equals 1. We get -3 minus 1. Absolute value of -4 is 4. So I have 3 points. I think that's enough for us to graph. So our first point is going to be at y equals 1, which is our y-intercept. And then our next point is going to be at -1, 4 and 1, 4. I'm going to connect these points from left to right. It just looks like your normal parabola. And this can definitely happen because whenever you have a parabola that's above our x-axis and is pointing upwards, if I take the absolute value of this, it's going to be the same because all of our y values are positive anyway. If all of your y values are positive, then your graph won't change if you take the absolute value of it. The very last thing we're going to do is write our domain and range, which is -infinity to +infinity for your domain. For your range, the lowest point is at 1, and it goes on to infinity. And for your piecewise function, the only thing that we really need to write is that for the equation of this graph, and this is going to be -3x squared minus 1. Why is that? It's because if I were to distribute this negative, I'm going to get 3x squared plus 1. And if you take a look at this equation, this clearly describes this graph. This is saying that we have a vertex at 0, 1, which we do, and our shape should face upward, our arm should face upward because of this +3 in front of our x squared. Before I set you free on doing the extra practice questions, I want you to try a question that's like this. Let's just say you're given a graph and they call it y equals f of x. And they said that this point is 0, 1. And you're trying to find our y equals the absolute value of f of x graph. Once you need to do this, all you have to do is take anything that's below the x-axis and reflect it back up so it's above the x-axis. So this portion over here, I'm just going to reflect this back up above the x-axis, and everything else is going to stay the same. So let's just say I had those two arms that look like this. Those stay the same because it's already above the x-axis, but that highlighted portion I have over there, it's going to reflect back up into +1 instead of -1. So the point at 0, 1, the same shape is going to follow like that. Here's another quick example. Let's just say instead I had a linear graph that looks like this. If I want to find the absolute value of f of x for that graph, anything above the x-axis stays the same. So this arm is still the same. And instead of the left-hand side of x equals 1 going down, it's going to go back up. I'm going to have a point at 1. So this portion of my arm is going to reflect back up above the x-axis. And that would